Hi class, we're going to finish off the chapter today, 2.7, Chemical Nomenclature. Derive names for common types of inorganic compounds using a systematic approach. So in the previous chapter, we talked about the ions that we can, that are from the periodic table, monoatomic ions. And those are going to be some of the most common ions that we deal with. And then there are the polyatomic ions, including the oxy ions that were in that chart that we saw before, that needs to be memorized, of positive and negative ions that have multiple atoms that make them up. Okay, so let's just start with the word nomenclature. That's just a way of saying a collection of rules for naming things. Compounds are identified by both their formula and their name. How will we learn to name the following types of inorganic compounds? Ionic and molecular binary compounds composed of two elements, ionic compounds containing polyatomic ions, and acids. Name the cation first, followed by the name of the anion. So, in the case of sodium chloride, for example, it's sodium is the cation and chloride is the anion. So we don't say chloride sodium. We don't say bromo-lithium. We say lithium bromide. A monoatomic cation is just given the name of the element. So sodium is just called sodium, but the anion is given a different name. It's not chlorine, it's not sodium chlorine, it's sodium chloride. A monoatomic anion is given the name of the element with its ending replaced by the suffix "ide." So the common monoatomic anions would be oxide, fluoride, sulfide, nitride. I just go down the periodic table of the non-metals that are going to absorb the electrons. They're all ides. Let's see. Beware the ides of halogens. Okay. A polyatomic ion is just given the name of the ion. Okay. So if you've got sulfur with 4 oxygens on it and has a 2 negative charge, it's called sulfate. If it's got 3 oxygens on it and it has a double negative charge, it's called sulfite. Which basically means you need to memorize it. Okay, so names of some ionic compounds. Sodium chloride, potassium bromide, calcium iodide, cesium fluoride, lithium chloride, sodium oxide, cadmium sulfide, magnesium nitride, calcium phosphide, aluminum carbide. Something to note in ionic compounds is that we don't make any allowance for the number in the formula, the number of sodiums in the formula, the number of carbons in the formula, the number of phosphoruses in the formula. We will be accounting for the number in molecular compounds, but not in ionic compounds. Names of some polyatomic ionic compounds. Potassium acetate. So we don't say potassium carbide hydride oxide. No. This whole ion, polyatomic ion, has a name. It's acetate. So it's potassium acetate. Ammonium chloride, ammonium being the polyatomic, in this case, anion. I'm sorry, polyatomic cation. Okay, sodium bicarbonate, HCO3 is bicarbonate. And although they call there's several others that are like hydrogen sulfate and hydrogen sulfide. They also have the alternative name of bisulfate and bisulfide. Okay, calcium sulfate, aluminum carbonate, magnesium phosphate. Again, no accounting is made for the number. It's not magnesium diphosphate. It's not, although there's a bi in there. It's not aluminum tricarbonate. It's aluminum carbonate. And the reason for that is that being electrically balanced, we already know how many carbonates there are to satisfy aluminum. We know that because they have well-known charges. Aluminum has a well-known +3 charge, and carbonate has a well-known 2- charge, and so on and so forth. So it's just these ionic compounds. No indication is made of the number of magnesiums, the number of aluminums, the number of carbonates, the number of sulfates that are within them. Most of the transition metals and some main group metals can form 2 or more cations with different charges. The charges of the metal ion is specified by a Roman numeral in parentheses after the name of the metal. So this compound, FeCl2, is iron 2 chloride, meaning that it has a 2+ charge. Iron 3 chloride, on the other hand, has a +3 charge. This one is a little bit strange. Even though Hg sub 2 has a 2+ charge, that 2+ is distributed among 2 mercury atoms. So each one, it's as though each one had only 1 charge. So it's a mercury 1 is the name of the mercury ion, and oxide. Mercury, without the subscript 2, it also bears a 2+ charge, but this is on only 1 mercury atom, and so it's a mercury 2 oxide. Tin can be in the state where it has a 2+ charge or a 4+ charge. Again, once we specify this, we already know how many charges there are, or what the ion looks like. When we say mercury 1, we know it's Hg sub 2. We already know what the ion looks like. We already know what this ion looks like, and we know how many are needed here to balance the charge over here, and so we don't put any word indicating how many of each are in each. However, we need to know these nomenclature prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. These are Latin prefixes for numbers. So, and oftentimes mono is omitted. We'll come across this not only in molecular compounds, but we'll also come across this in hydrates. Okay, Aaron Brockovich found that chromium-6 used by PG&E had contaminated the Hinkley, California water supply. The chromium-6 ion is often present in water as the polyatomic ions chromate and dichromate. Right. So this is chromium here with two oxygens that is in the 2+ state and two oxygens that are in the, they're also in the 2+ state, but this forms a polyatomic ion with a 2- charge. And this also forms a polyatomic ion with a 2- charge. So, hydrate. A compound, often ionic, that contains one or more water molecules bonded within its crystals. Hydrates may typically be dehydrated by heating to remove the bound water molecules, yielding the anhydrous compound. To name hydrates, name the anhydrous compound and add the word, okay, I said Latin, I guess it's Greek, prefix denoting the number of water molecules. So the formulas for hydrates are written by appending the formula for the water to the formula for the anhydrous compound, including a stoichiometric coefficient denoting the number of water molecules separated by a vertical centered dot. For example, copper 2 sulfate pentahydrate. It means it's got 5 water molecules. Copper sulfate dot 5H2O. Calcium chloride monohydrate. CaCl2 dot H2O. I tell you what, let's do a quick search here of hexa. Okay, it is a Greek root. Okay, etymology. Oh, Latin. Okay. Okay. So let's do mono. Etymology. Okay. Die as a prefix. I still say it's probably Latin. I'm going to investigate it more, but I think they might be wrong. Okay. Naming binary molecular covalent compounds. Now this is where a bond is formed. And because a bond is formed, you can't simply rely on neutrality in order to determine what the formula for the compound is. Molecular compounds are named using a different set of rules. Covalent bonding allows for significant variation in the ratios of the atoms in a molecule. The names for, I'd change the word to formula here. Covalent bonding allows for significant variation in the ratios of the atoms in a formula. The names for molecular compounds must explicitly identify these ratios. The name of the more metallic element, the one farthest to the left and bottom of the periodic table, is named first. So, like the metals first, sodium or whatever. But in the case of carbon, whatever. Followed by the name of the more non-metallic element, the one farther to the right or top, with its ending changed in the suffix to So, water, for example, hydrogen is more to the left side of the periodic table, and oxygen is to the right, and the numbers of atoms of each element are designated by the Greek prefixes. So, it has been proposed that water should be called dihydrogen monoxide. Di, meaning two atoms of, hydrogen, which is on the right side of the periodic table, mono, for one, oxide, so dihydrogen monoxide. And I have seen, there's been a lot of joking about dihydrogen monoxide because it sounds like it'll kill you, and to be fair, you can drown in water, it will kill you. Okay, when only one atom of the first element is present, the prefix mono is usually not used. So, carbon dioxide, for example, we don't call it monocarbon dioxide. We just call it carbon dioxide. Now, if there were two carbons present, we might say something. When two vowels are adjacent, the A in the Greek prefix is usually dropped. Okay. So, two vowels like monooxide becomes monoxide. So, here are some names of molecular compounds composed of two elements. Sulfur dioxide, sulfur trioxide, nitrogen dioxide, dinitrogen tetroxide, dinitrogen pentoxide, boron trichloride, sulfur hexafluoride, phosphorus pentafluoride, tetraphosphorus. Oh no, they didn't follow their own rule. Decaoxide. Looks like it should be decoxide, because by the rule that they had before. Iodine. Oh, this is completely wrong. This is Oh, it's the same thing. They wanted to represent another compound there. Oops. They wanted to write here F, hepta is 7, and iodine, is I. Iodine heptafluoride, phosphorus decaoxide. Okay? So, they didn't do that there. Alright, boom, boom. Some compounds containing hydrogen are members of an important class of substances known as acids. Many acids release hydrogen ions when dissolved in water. A mixture of an acid with a water is given a special name to denote this property. The word hydrogen is changed to the prefix hydro. The other non-metallic element is modified by adding the suffix "ic." The word acid is added as a second word. I have to disagree with this a little bit. Only if the polyatomic ion is an 8 is the suffix changed to "ic." If the polyatomic ion were an ite, the suffix is changed to us, O-U-S. But let's see what they have to say here. The name of the gas is hydrogen fluoride, and it forms hydrofluoric acid. Hydrogen chloride, it forms the water acid hydrochloric acid. The gas, hydrogen bromide, then its acid is hydrobromic acid. Hydrogen iodide is hydroiodic acid, and hydrogen sulfide is hydrosulfuric sulfuric acid. Now, don't confuse this with sulfuric acid, which is something else entirely. Here we go. Oxyacids. Compounds that contain oxygen, hydrogen, oxygen, and at least one other element, and are bonded in such a way as to impart acidic properties to the compound. Typical oxyacids consist of hydrogen combined with a polyatomic ion, oxygen containing an ion. To name oxyions, omit hydrogen, start with the root name of the ion, and replace ate with ick or ite with us, and add acid. Okay, so let's go back here. These are simple acids, diatomic acids that have a gas and they form an acid. These others are polyatomic ions, and those we don't use the word hydro. So, names of common oxyacids. Acetate, it forms acetic acid. Nitrate, it forms nitric acid. Nitrite forms nitrous acid. Perchlorate forms perchloric acid. Carbonate forms carbonic acid. Sulfate forms sulfuric acid. Sulfite forms sulfurous. Did I say that right? Sulfate forms sulfuric acid. Sulfite forms sulfurous acid. And phosphate forms phosphoric acid. Okay. That is the end of the chapter. We'll go over the exercises in class. Thank you very much.